In this video, we will be discussing functions. First, let's determine whether a relation represents a function. A relation is a correspondence between two sets. If we let x be the input, or in other words, the domain, so let's let this set of data points be the input, which is also called the domain. We will let y be the set of points that is the output. We will also call that the range. We can show relations with equations, graphs, or maps. This would be an example of a map. For example, what if I said the input of buying gas at a local gas station, the input would be the gas station that you select you want to go to. So for example, you have the choice. You could go to Family Express, you could go to Speedway, you could go to BP, you could go to Shell. So all of those options are in your hometown, and you have all those options as an input as to what you will get for gas. The output is going to be the cost or the price. So in this case, X is going to be the name of the gas station, and the output is going to be the price of gasoline at that location. Let's say you go to Family Express and the gas costs $2.49. This would be one relation between Family Express and the cost of the gas at that location. Let's say Speedway, the cost of gas is $2.65. BP, the cost of gas, is $2.59. And Shell, the cost of gas, was also $2.65. So this would be an example of a relation between the name of the gas station and the price of the gasoline at that gas station. Again, the input or the domain is a set of all points in your X that give you the output or the range, which is the set of all points in your Y. Moving on, let's talk about the definition of a function. If we let X and Y be two non-empty sets, non-empty means there has to be points in here. It cannot be vacant. So if both X and Y are non-empty, a function from X to Y is a relation that associates each element of X has exactly one element of Y. In other words, no input can have more than one output. You'll notice each of these points have one and only one output. Family Express has one price. Speedway has one price. BP has one price. And Shell has one price. They all go one direction. So what that means is the input cannot have more than one. In other words, Shell cannot have two lanes coming out of it, because if it did, it would point to two different points in the output or the range, but yet each input can only have one particular price. Shell cannot have two prices for one type of gas. It can only have one. So if you had two maps coming out of the input, that would indicate that it is not a function. So let's look at a few examples and determine whether these represent a function. Down here we have 4 different points, and we're asked to determine whether these 4 points represent a function. Well, remember, no input can have more than one output. So what we're looking for are any x's that might have more than one particular y. No ordered pairs can have the same first element but different second elements. So for example, if we look at these 2 points, you see that the input of -1 would go in the first circle. The output, this -1 says the y output should be 0. But this point says -1 input should go to 3. That is an example of not being a function. It is not a function because one input goes to 2 different outputs. Let's look at this one. 1 goes to 1, 3 goes to 1, -1 goes to 3, 4 goes to -3. Those are okay because we have all different elements in the inputs, and all of those different inputs go to a particular y or range. It's okay that some of them share an output. So for example, if we look at these 2 points, it says that the point 1 is going to go over to y is 1. It also says 3 goes to 1. So I have 3, it also goes to 1. Now this is a function. A function says you can have separate x's going to the same y, but you cannot have one x that goes to 2 different y's. So there is a difference. So let's look at some examples of different functions down here, and let's try to determine whether they are or are not functions. So let me give you an example. What if I have 1, 2, 3, and we have the points 4, 5, 6. And my map looks like this. So 1 goes to 5, 2 goes to 4, 3 goes to 6. This is a function. What we're looking for is an x that goes 2 different directions. And none of these x's go to 2 different y's. Down here, a function. Let's say let's increase and put an extra number in our domain. So 1 goes to 6, 2 goes to 5, 3 goes to 7, and 4 goes to 6. So it looks like both 4 and 1 both go to 6, but that is okay. You can have 2 different x's going to one y, you just can't have one x going to 2 different y's. Let's try one over here. What if I have 1, 2, 3, 4, and 5? So here we've got 1 goes to 4, 3 goes to 5, and I don't have 2 being mapped to go anywhere. This would be an example of not a function. It is not a function because for every input there has to be an output. The definition that we set up here says every x has exactly one y. This x does not have a y, so therefore it is not a function. One more. What if we have 1, 2, 3, and we have 4, 5, 6, and let's say 1 goes to 4, 2 goes to 4, 2 goes to 5, and 3 goes to 6. This would be an example of not a function, because you see the input 2 goes 2 different directions. It has 2 ranges or 2 y's, 2 outputs for only one x. So moving on to the next page, you can tell we're trying to determine whether an equation is a function. In order to determine whether an equation is a function, first, if you're going to solve an equation for y, and more than one value of y can be obtained for any given x, then it is not a function. So for example, we have this equation where y equals negative 1/2 x minus 3. Well, if we graph this, we could graph it straight from here because this is slope-intercept form, or we can make a table to determine points and able to graph it. Either way, if I made a table of points, I could plug in values like 0 and get negative 3. I could plug in 2 for x, and that would give me negative 4. If I plug in 4 for x, that would give me negative 5. So this will give me an idea of what the graph looks like. So this is the graph of a line, a linear function, and I know that the y-intercept is negative 3 and the slope is negative 1/2. And I could tell all that in the graph by using either the table or slope-intercept form. Now the question is this a function? Well, to be a function, every x can have only one y. So you see this 0 would map to negative 3. 2 would map to negative 4, and 4 would map to negative 5. So for every x, there is exactly one y. So yes, this is a function. Now when we look at the second one, let's make another table. For example, if I plug in x is 3, and I solved this, it's a little backwards because x is on the other side. Let's subtract 1 from both sides. Let's divide by 2. And if we take the square root of both sides, I get y equals plus or minus 1. So when x is 3, y is 1. It's also negative 1. So this 3, this domain, is going to a range of 1, but it's also going to negative 1. So this would be an example of something that is not a function. The graph of this actually looks like 1, 2, 3 is actually a parabola leaning on its side. This would not be a function because you see for this particular x, when x is 3, you have 2 y's. So let's find the value of a function. If I say I have a function and I'm going to call it f of x. That's what f parenthesis x means. It means f of x. So it means the value of f at the number x. So this is the name. The input is x, and we'll input that into the function f of x, which will be the output. So f of x is the output, input is x. In this case, f of x is your y. So x is your input, y is your output, but sometimes when it's a function, we designate the output as f of x. So let's look at what that would look like in a few examples. So down here we have some examples. For the function f, defined by f of x equals negative 3x squared plus 2x. Let's find the following. So what this is saying is go to the function f. Here is the function f. Now in that function f, right now, f of x is equal to negative 3x squared plus 2x, meaning x is plugged in for all of the x's. Well, if we want f of 3, then we take 3 and we plug it in for all of the x's. So f of 3 is going to be negative 3, and again we take 3 and we plug it in for the x's. So it'll be 3 squared plus 2, and again plug 3 in for the x, and then we simplify. So f of 3 equals negative 21. Now remember, this is the output. 3 was the input. So the input was the number 3, which was designated by this number here. We took 3 and we plugged it in for x as my input. When you input the number 3, your output will be negative 21. Clearly, if I plugged in a different input, I'll get a different output. This one says, let's take f of x and add f of 3. F of x was already determined by the problem up here. F of x is all of this. It means x is plugged in for x. So f of x is the original problem. Then we're going to add to that f of 3. Well, f of 3 we already figured out. It's all of this, which is negative 21. So when I simplify all of that, I get negative 3x squared plus 2x minus 21. So this is my output. F of negative x tells me to plug negative x in for x. So we get negative 3 times negative x squared plus 2 times negative x. Well, when I square a negative, that becomes positive, but I still have the negative 3 out front. 2 times negative x is negative 2x. This time the negative is not inside, it's on the outside. So we treat it as a multiplication. So we calculate f of x first, which is everything that's up here. So f of x is negative 3x squared plus 2x. Then we take a negative and we throw it in front of that whole function. So we distribute that negative sign inside, and it becomes 3x squared minus 2x. F of x plus 3 tells me to take x plus 3 as my input and plug it in everywhere there is an x. So it becomes negative 3, x plus 3. Then we square that, plus 2 times x plus 3. So this is going to be a FOIL problem. So this is actually negative 3 times x plus 3 times x plus 3 plus, I'll go ahead and distribute this, to x plus 6. So let's FOIL 3 times x squared plus 3x plus 3x, so that's plus 6x plus 9. Distribute the 3, so 3x squared plus 18x plus 27 plus 2x plus 6, and then we combine like terms, so that gives me 3x squared, 18x, and 2x is 20x, and 27 and 6 is 33. There was a negative sign. I lost a negative sign over here. There was a -3 here, -3 here, and then I lost it. So right there, I've got to add that back in. So this becomes -3x squared minus 18x minus 27. So that becomes, down here, let me correct this, that becomes minus 3x squared. Negative 18x plus 2x is a negative 16x. Negative 27 plus 6 is a negative 21. Let me rewrite that. Negative 3x squared minus 16x minus 21. Very easy to make those negative mistakes. All right, last one. The last one down here is the function f of x plus h. So we'll do f of x plus h. So we're going to take x plus h and plug it in everywhere there is an x. So this becomes -3. I won't lose the negative this time. So -3 times x plus h squared plus 2 times x plus h. So we're going to do the same business that we did up here by foiling all of this out. So let's see what happens. -3 x plus h times x plus h plus 2x plus 2h. When I FOIL this out, I get -3 times x squared plus xh plus another xh, so that's 2xh plus h squared. When I distribute the 3, I get -3x squared minus 6xh minus 3h squared plus 2x plus 2h. And then I ask myself, is there anything I can combine? Are there any like terms in the statement? And I do not see any like terms. So that is my final answer.